So this lesson's about vector equations of lines, the angle between two lines, and also constant velocity problems. So I'm going to start by examining our y equals mx plus b, which I've written a little bit differently because we're about to write the vector equation of a line. And so I have some thoughts ahead of, I'm thinking ahead. So if you examine it a little bit, the b was the y-intercept, which if you think about it was just some arbitrary starting point. It happened to be on the y-axis, but it didn't have to be. M was the slope, and if you think about what slope does, rise over run, it's giving you directions of how to move forward and get new points. And of course, x is some input variable that you need to identify how far along the directions you want to go, and then y is the output value. So now let's examine the same kind of principles with vectors. Let's say we had a starting point at point P, so we could then have a direction vector that took us from the origin to point P to tell us where to start. And then we would have this vector that's telling us the directions. In fact, that's called the direction vector. And then if I started at P and went by the direction vector, I would get to a new point Q. And then to get to any arbitrary point R on the line, I would, again, start at P and then take some number of vectors V, in this case 2 vectors V from there to get to the point R. So here's the vector version of that. So R is the final position vector. It's like your output Y. It's the final position vector for any point on the line. We start with the initial position vector, A vector, which took us to the very first point, which could have been the y-intercept, but didn't have to be. And then we added on, then V was the direction vector, which is kind of like the slope, only it actually gave us a direction to follow, times a parameter or a real number, which here we're going to use lambda. That's the Greek letter lambda. Lambda has to be a real number. It's called a parameter. It's kind of like using x, except it isn't x because x and y now are going to be in the R and in the V and in the A because they're vectors pointing in both x and y direction. So you have to use a different parameter or variable here, which we're going to call lambda. So the final position vector equals the initial position vector plus parameter times the direction vector. Now, you may notice that the direction vector has a particular magnitude associated with it, and of course it has a direction. But if you have a longer direction vector, you could still get the same line. You would just be then using different lambda to get to a specific spot. So this equation of a line is by no means unique. The y equals mx plus b slope-intercept version of the equation of a line is going to be unique for a specific line, but this one can't be. So I now want to show you how there's actually multiple versions of this that you can come up with. So this is the vector equation of a specific line. This vector xyz is the output vector or the r vector, the position vector for any point. It'll have an x coordinate, y coordinate, z coordinate, the output variables here. 3, 2, -5 is the starting position or starting vector or starting location. Lambda, of course, the parameter, and then 4, 1, 3 here is the direction vector for this particular line. But I can write this exact same information this way. X equals 3 plus 4 lambda, y equals 2 plus lambda, and z equals -5 plus 3 lambda. And I got that by basically matching up the x's, the y's, and the z's. This is the same information, but these are called parametric equations of the line. So the first one was called the vector equation of the line. These are the parametric equations of the line. Now I can do one step further. I can solve each of these for lambda. So for example, I can get lambda equals x minus 3 and then divided by 4. Then I can get lambda equals y minus 2, and I'm gonna write divided by 1. And then I can get lambda equals z plus 5 and then divided by 3. And then since they're all equal to lambda, I can set them all equal to each other and get x minus 3 over 4 equals y minus 2 over 1. And you could drop that over 1 if you want to, but there is a reason why I usually like to keep it. And then z plus 5 over 3. So these are called the Cartesian equation of that line. And what it has done is it has eliminated the parameter and it's eliminated vectors as well. It only has the x and y and z coordinates for any point along the line. Now, although this is usually not the most useful, you can always go back to parametric if you basically solve for x, y, and z. You just set each of these equal to the parameter. You can call it lambda or mu or whatever, t, s, doesn't matter, just not x, y, z. And then just solve for each of the variables and then go back to parametric, and then you can make vector equations that way. Occasionally, you might actually want to work with that anyway. And hopefully, the switch back and forth between parametric and vector is relatively straightforward. All right, let's find parametric equations for the line through A and B, and the coordinates are given. So first of all, I'm going to just arbitrarily pick A to be the starting point and never said it couldn't be. And then if I go from A to B, that gives me a direction vector. So let's start with the vector AB. That's B minus A. So that's going to be negative 1 minus 2 is negative 3. 0 minus negative 1 is 1. And then 2 minus 4 is negative 2. So that's my direction vector. And then my final position vector, or r vector, I could call it x, y, z, or I could call it the r vector if you want, is going to equal the initial position vector we said it was going to be. We're going to go to A. So OA vector will be initial position. So 2, negative 1, 4 is the vector that gets me there. Plus, I'm going to use lambda for my parameter because that's the one that I'm used to. And then times the direction vector, which was the AB vector, negative 3, 1, negative 2. And so that's the vector version, but the parametric version of that would be x equals 2 minus 3 lambda, y equals negative 1 plus lambda, and then z equals 4 minus 2 lambda, and I got that again, x equals 2 plus lambda times negative 3, y equals negative 1 plus lambda times 1, z equals 4 plus lambda times negative 2. So there they are, the parametric equations of the line. They're not unique because I could have used a different direction vector. I could have gone the other way. I could have made it longer or shorter. The direction, they would have to be parallel to this one though. And then I also could have started here instead of over here. It doesn't really matter. I could have started anywhere along the line. It doesn't make any difference. So now let's talk about the angle between two lines. We're assuming that these lines are going to intersect, otherwise you get yourself in a little bit of trouble because you can't really measure angles. But as long as the lines intersect, if you have, let's say, line 1 looks like that and line 2 looks like that, there's actually two different angles between the line. There's that one, and then there's that one. Now this is also one, but these two are vertical angles, so they're the same measure. And these two are also vertical angles, so they're the same measure. There's really two different measures you could be calculating for the angle between the lines. So sometimes you just be asked for find the angle, which really means just find an angle, or it might ask you specifically find the obtuse angle or the acute angle. So you have to make sure if you get the wrong one, they're supplementary so you can find the other one. Now to find those angles, what we're going to do is we're going to find the direction vector for each of those lines. And once we know their direction vectors, we can use the dot product method of calculating the angle. So that's what we're going to do. So here we go. Find the angle between L1, which is x equals 2 minus 3t, and y equals negative 1 plus t, and L2, which is x equals 1 plus 2s, y equals negative 4 plus 3s. Now they've used here the parameter t for the first line, and you should always do this. Use a different parameter for the second line because you do not know ahead of time how the parameters are going to interact with each other. So you don't want to use the same parameter twice. Each line gets its own parameter. Now, if I look at this set of parametric equations, remember if I write it into vector form, I would have the 2 and the negative 1 would contribute to the initial point or the initial position vector, and then the negative 3 and the positive 1 would contribute to the direction vector. So let me call that vector v1 for the direction vector for line 1. It's going to be negative 3 in the x direction and 1 in the y direction. Those are the coefficients there. And then v2, which is the direction vector for the other line, well, that'll be 2 in the x direction and 3 in the y direction. So 2, 3, because again, the 1 and the negative 4 just help you figure out the initial point or the initial position vector. So to find the angle between these two lines, if I just find the angle between these two vectors, I've answered the question. So first I do v1 dot v2, and I get the dot product is going to be negative 3 times 2 plus 1 times 3, so it's negative 6 plus 3, which is negative 3. And then I need to magnitude of v1, which is the square root of negative 3 squared plus 1 squared, which is root 10. And then magnitude of v2 is another one I need. Square root of 4 squared plus 2 squared plus 3 squared. which is going to be square root 13. And so again, the dot product, v1 dot v2, equals the magnitude of v1 times the magnitude of v2 times the cosine of theta. And so I can plug all the numbers in and isolate cosine theta. So I have -3, and then I'm going to divide by the two magnitudes multiplied together, is going to be square root of 130 equals cosine theta. Right, the 130 is the square root 13 times the square root 10. So now I can do cosine inverse of that, and I will get my answer. So theta equals cosine inverse of, and it didn't say radians or degrees, I'm just stick with with degrees because that's what the textbook seems to be doing on these. So cosine inverse of -3 over square root 130, which gives me 105. I'm going to go with 105.3. Now, if the specific question had said find the acute angle between these two, then I would have to say, well, this is an obtuse angle, but I know there's a linear pair, so I'd do 180 minus that and get the correct answer that way. All right, here we're asked to find the obtuse angle between these two lines. Well, first of all, I'm not going to worry about obtuse and acute. That's the last thing I'm going to worry about. I'll fix it if I have to. These do not look like vector equations, though, so let me rearrange them so they're y equals mx plus b. Y equals -2x plus 5, and on the other one I get -2y equals -3x plus 8. I divide both sides by -2, so really y equals 3/2 x minus 4. Now remember, the y-intercept here is like the initial position vector, so I don't really need that. The slopes are like finding the direction vector. So if I think about this slope, let me write it as -2 over 1. What that's saying I'm supposed to do, so let's call it vector v1. What it's saying I'm supposed to do is to go down 2 and right 1. Well, to go down 2 and right 1, that would be the vector 1, -2. And then this one over here is saying, let's call that one v2, is saying go up 3 and right 2. So again, up 3 and right 2 would be the vector 2, 3. So now I've got two direction vectors that I've generated from looking at slopes, and I can do their dot product and then work out what happens from there. So here we go. v1 vector dot v2 vector is going to be 1 times 2 plus -2 times 3, which is going to be -4. And then the magnitude of v1 is going to be the square root of 1 squared plus -2 squared, which is root 5. And the magnitude of v2 is going to be square root of 2 squared plus 3 squared, which is going to be root 13. And so finally we can say v1 dot v2 is going to be magnitude of v1 times magnitude of v2 times cosine theta, and I can isolate cosine theta, so cosine theta is going to equal, the v1 dot v2 was -4, and I have to divide by the product of the two magnitudes, so square root 13 times square root 5, which is really square root 65. And now I'm going to get an obtuse angle here because cosine is negative, so that's good. So theta is cosine inverse of -4 over square root 65, which is going to be 120 if you go to 3 sig figs. It's actually 119.74488, etc., but I'm going to go with 120. So now we're going to do some what are called constant velocity problems. We have an object's path is given by the vector equation. Xy is the location of the object at any given time. 1, 9 is the original place where it started, the position vector for that, plus t times 3, -4. So 3, -4 is going to tell you how to move in that two-dimensional space. T is going to be the time measured in seconds. T is going to be greater than or equal to 0, so we're not going to go back in time. And then all the distances are going to be measured in meters. So first thing is to plot the path of the object for t equals 0, 1, 2, and 3. Now, since I already know what this is going to look like, I've generated the grid that fits. Probably should have done this on graph paper because it did say plot, but I'm going to do the best I can. So when t equals 0, I plug in 0, I get 1, 9. So that's the point right there. That's the t equals 0. Let me label it t equals 0. And then when t equals 1, I get 1, 9 plus 3, -4. So I get 4, 5. So 4, 5 is right there. That's the t equals 1. And then when t equals 2, I get 1, 9 plus 6, negative 8. So it becomes 7, 1. So 7, 1 is about there. That's the t equals 2. And then finally t equals 3, I get 1, 9 plus 9, negative 12. So it's going to be 10, negative 3. So that's about right there. So that's a t equals 4. Oh, sorry, t equals 3. And again, if you had put the grid on there correctly, you would have had that. And so the path of this object is, this second point looks a little bit off, but anyway, path look like that. And if you think about it, it's moving in that direction. We know it's moving in this direction because that time is increasing. So let me make these a little bit bigger so it's clear where they are. So that would be the plot to plot the path of the object between t equals 0 and 3. Now the question says find the object's velocity vector. Well, velocity is measured in meters per second and has direction associated with it. Time is being measured in seconds. Distances are being measured in meters. So the direction vector, this one right here, literally is the velocity vector. It's telling us how to move. We went right 3 and down 4 to get from this point to this point. We went right 3 and down 4 to get to this point, right 3 and down 4 to get to this point, etc. So the velocity vector, let's call it v, in this case is literally the direction vector because the distance were being measured in meters and time was being measured in seconds. Now, if there was some other thing going on, we would have to take that into account, factor stuff out or whatever to make those units match up. Now it says find the object's speed. Well, speed is just magnitude of velocity. So the magnitude of the v vector is going to be the square root of 3 squared plus negative 4 squared, and you might recognize that. It's going to be 5, and the units for speed are going to be meters per second. And so that's that one. So sometimes I get students ask me the question, when am I going to need to know this? What practical application does this math have? What am I going to use it for? And although I think that there are other reasons to learn math as well, such as, it's elegant, it's interesting, it's fun, I do also understand that, math can be practical, and that's a valid question. And so when I saw this problem in the textbook, I was blown away. I would never have thought of it. However, once I saw it, it was obvious. Like, this is something, I can't speak for the rest of you, but I run into this all the time. So, good job, textbook. That was very creative. I'm really impressed. Let's take a look. A mermaid is initially at the point 15, 8, negative 1. She swims with velocity vector 3i hat minus 5j hat minus 9 halves k hat meters per second. Find her position after t seconds is the first thing. So first of all, if I want the position after t seconds, that's essentially asking me to find an equation for the motion of this mermaid. So I'm going to use a vector equation given that their stuff is given to me in vectors, at least the velocity vector. So initially, I have this point where she starts at 15, 8, negative 1, and I'm going to create a position vector to get to that spot for my starting location. And then the velocity vector then will become the direction vector, especially since it's measured in meters per second. That means that every 1 second, this is the motion that is going to occur, that the mermaid's going to have. So let's start with the vector x, y, z for the position vector at the end. I could also just use the r vector equals. So the initial position vector gets us to that point. So it's 15, 8, negative 1 plus, and then t for the time multiplied by the velocity vector or the direction vector 3, negative 5, negative 9 halves. So this equation here, this vector equation, would give her position after t seconds. So, you can plug various values of t in there to work it out. So part B says find her speed. Well, speed is just the magnitude of velocity. So let's just do that. So the magnitude of the velocity vector is going to be the square root of 3 squared plus negative 5 squared plus negative 9 halves squared. And after plugging that into the calculator and rounding it to the regular 3 sig figs, you get approximately 7.37 meters per second. And then the final question is, when will she reach a depth of 28 meters? So depth is the z component, and a depth of 28 would actually mean that she reaches negative 28 as far as the z coordinate is concerned. So let me just focus on the z coordinate, or the z parametric equation involving z. So z equals -1 minus 9 halves t, and I want the z to equal negative 28. So I'm going to plug negative 28 in there. So negative 28 equals -1 minus 9 halves t. Add 1 to both sides, so negative 27 equals -9 halves t. And when I multiply both sides by -2/9, the 9 and the 27 partially cancel, and you multiply by 2, so you end up with 6 equals t. So after 6, and the units were seconds. And that's the end of that example, and that's the end of the lesson.